Hi, welcome to the last session of the day, which is going to be about search engines and how they can be more or less microservices. So the agenda would be to go over the main workloads, kind of from the infrastructure standpoint. We'll start with stateless workloads. We'll go to distributing the configuration and handling the cluster state. And then the stateful workload, of course, the actual data distribution, and then how they monitor everything. And because the focal point would be Vespa, I'll talk a bit about how you can run Vespa in Kubernetes today and how that might evolve in the future. So to clarify the search engine vector DB kind of space, I'm thinking about information retrieval. So we have a corpus of documents. We want to extract something relevant out of it. This could be through keyword search. This could be through semantic search, like vector search. Could be RAG, could be recommendations, or like data analytics, like we can use grouping to see what's in that corpus in real time. So this is the space that I'm referring to. And there are lots of tools that are in this space, and I think that the list keeps growing. And I wanted to ask if you have experience with the Lucene search engines, either Elasticsearch, OpenSearch, or Solr. Can I get a show of hands? Oh, this is awesome. Because that's also most of my professional background. I've been working with those for more than 10 years at a company called Sematext. But I recently joined Vespa.ai, and Vespa is an open source search engine, also kind of in the information retrieval space, not exactly overlapping in terms of use case with the others, but there's quite a lot of overlap. So what I'll do today is I'll talk a lot about the architecture of Vespa, from an infrastructure standpoint, and compare that to my point of reference, which seems to be yours as well, which is like how Elasticsearch and the rest work. And by the way, how many of you have heard of Vespa or worked with Vespa? Can I get a show of hands? Okay, so this will be new to you, I think. Vespa, right. Well, we're Vespa.ai, that's the distinction. And there are other, as I said, a lot of tools in this space. I won't touch them, but just wanted to acknowledge that we're not the only ones. Okay, so the tasks that that we're looking at, obviously there's a lot of data that has to be potentially distributed. We may need to take care of fault tolerance and things like that. That I think is obvious. What may be less obvious is that we also have to do a lot of stateless processing. Like, when we process queries and documents when we're writing, and this, I think, is increasingly complex. And I'm also going to talk about the configuration, meaning like distributing the schema and other things to all the nodes and making sure we know which node is alive and which one is not, things like that. And of course, monitoring everything, right? So this is the focus. So I'll start with stateless workloads. So let me give you some examples to put some flesh on that idea. So for example, when we write documents, we may want to do some processing like, let's append a timestamp. Or if we want to generate vectors, for vector search, we can generate those embeddings from text or from images. We'd use a machine learning model. So that is stateless processing effectively. At query time, we can do some custom query parsing. We can apply our business logic. One of the things that has to be done with distributed systems is to distribute the query to all the nodes that hold data and then gather partial results into a final response that will then go to the client. That is also stateless processing. And we may also want to process results further. So for example, during RAG, right? Like you'd send the query with a prompt to Vespa, for example, and then Vespa can send those results with the prompt to an LLM. The LLM can be remote or could be hosted in your Vespa cluster and then stream the reply back to the client, right? So this kind of processing is stateless in essence, and we can deal with it separately than we do with the stateful part. Okay, how do these search engines do it? Well, with the Lucene search engines, there's this concept of node roles. So all the nodes will run off the same image, but you can configure them and say, this node shouldn't hold data, for example, right? And this is how this works. And stateless processing can be done by coordinator or specifically to writes by ingest nodes. Vespa has a different approach in the sense that nodes will have different services, and a service is a separate process, could be in a different language. Like in this case, the stateless processing is done by the Java stateless container, which is in Java, as opposed to the content node, which deals with data, that is a compiled binary from like C++ code. And if you're confused with the container terminology, this is for historical reasons, because this name came up about 20 years ago when Vespa kind of started in the way it is right now. It was open sourced in 2017, but the history is quite involved. Okay, let's move on to the next task, which is managing the config. And what do I mean by config? I mean all the metadata, everything that is not a document or not a query that's being processed. And I would make a distinction here between two sides of that metadata. So it can be a behavior definition. So how is the search engine supposed to react to input? So here we can think of things like schema, or when we generate embeddings, which model to use. So things like that, which define the behavior. And this is different than the current state of the cluster, right? So mostly we're thinking about data and like which nodes are up, which bit of data lives where. And that is also metadata that has to be managed. So Lucene search engines treat all this metadata pretty much uniformly, which is straightforward way to do it. So for example, Elasticsearch and OpenSearch, each node will have a copy of all the metadata, but only the cluster manager or master node is allowed to write to the metadata. So when a node joins the cluster or you change the schema, that's processed by the master or the cluster manager. And then it's the cluster manager's role to distribute all those changes to the other nodes. Make sure they got the updated thing. And then it also is responsible for pinging all the other nodes to make sure that they're up, right? Because otherwise it has to mark them as down. Solr has a slightly different approach in the sense that it uses Zookeeper to store all this metadata. But again, there's one node in the cluster, it's called the overseer, that is able to make the changes. And while we can scale Zookeeper for reads, we cannot scale it for writes, and the same is true for Zookeeper. So those might become bottlenecks if the cluster is large and or if we have a lot of metadata changes in the cluster. Vespa has a completely different approach. So first of all, it deals with the behavior separately from the cluster state. So I'll start with the behavior. The behavior definition goes into a set of files that make up the application package. So you can think of the application package as a Kubernetes resource. And we say we deploy an application package in the same way you would do kubectl apply. And when you do that, the configuration goes to the config servers that will store this configuration to Zookeeper. And then at runtime, every node, no matter what it does, will have this other separate process, which is called config proxy. And the config proxy will serve the configuration for that node. The config proxy will communicate by default to the config server to get the updated configuration, right? But it doesn't have to do that. We can also say, do not communicate. And if the config changes, I don't know, I'll restart you. With data distribution, this is a separate service that's called cluster controller. Like we have multiple cluster controllers in the cluster, they elect a leader, and it's the leader's role to keep an updated cluster state. So it will ping all the nodes that hold data, so those will be the content nodes, and it will know which one is alive and also which bucket of data lives where. And it can do some of that by looking at the ideal bucket distribution. So that is deterministic, which is, I find interesting. Like if you know how many nodes you have, then you pretty much know without looking which chunks of data should be where. And I want to talk a bit more about the distributed model of data of both kinds of engines to add some clarification. So you're probably familiar with how Elasticsearch and OpenSearch and Solr do it. So you have you can have multiple indices, and each index can have multiple shards, and then each shard can have a number of copies, right, replicas. And the idea is we can have more shards to distribute the data onto more nodes, and this will distribute both reads and writes to the other nodes, and you can also have more replicas to distribute only reads to all the nodes, and also that adds fault tolerance, right? So that's the trade-off. Let's see what happens when we add a new node. Well, we can migrate some of the shards to the new node. How does this work? From the leader or the primary shard, we create a new copy, or well, they do it, the search engine does it, right? Creates a new copy on the new node, and then when that is done, removes the old copy. And this will simply copy the files, which contains everything, like the index data structures there. But there's a bit of a race, because during that move, or during that replica initialization, you have to keep writing to the transaction log, because if something goes wrong, you need to be able to start over again. And this is why there's this practical limitation of how large a shard can be. You'll probably find advice on the internet, it shouldn't be over 50 or 100 gigs. That's the reason, because the transaction log can grow way too large when you're doing this move. So Vespa has this different approach, which you might find in like MongoDB or Cassandra, where we divide the document space into many small buckets. And these are like virtual buckets, because the actual data structures are per node, right? We don't actually have separate files for each bucket. So the data structures per node are a good thing for queries, because then you have only one data structure to go through when you do the query. We actually benchmark this. If you like Google for Vespa versus Elasticsearch performance, you'll see quite a lot of details. Like there's an 80-page document about it of precisely this kind of trade-off, which has lots of pros and cons. But the point is, when it comes to data distribution, we have this virtual bucket space, which means that if we add a new node, we can move, proportional number of buckets to the new node. But the problem is, we don't move the actual buckets of data. We have to reindex all the documents belonging to those buckets. So this is a more expensive process. We don't simply copy the files as we do with shards. That's the downside. The upside is we don't have to think up front about the number of shards that we need to have in order to have a balanced cluster, right? Because that's usually the bottleneck with sharded kind of search engines, in the sense that some nodes can become hotspots. Here, that's not so much a problem because data can be moved much more granularly. And we also don't have the transaction log problem, right? Because we have some buckets that were initialized in the new node, and then new data goes directly there. We don't have to wait for the shard to be initialized on the new node. Okay, let's move to monitoring. So all these search engines expose metrics API, and Elasticsearch and OpenSearch will also centralize the metrics for you. So if you hit one node, you can get all the metrics from the whole cluster. This, of course, is not free. Solr does it in a more simpler way. Like you hit one node, you get its metrics, and that's it. And Vespa does a bit of a mix. So again, there's a different service, which is called the metrics proxy, that exposes metrics and can also expose them in Prometheus format directly. It centralizes those metrics and can also cache them. With logs, the Lucene search engines, they're written in Java. It's like one process, by and large, per node. So that, with a default image, will log on standard output. You can use whatever specialized tools to centralize these logs, all very nice. Vespa has more of like an old school kind of approach, which is we have separate processes. They all use like this common logging module, and they all write to files. And then you have a process called logd, which has to handle the rotation of these files and forwards them to yet another process in the cluster called log server, right? So this could, in the future, be simplified to just let's write to standard output and let the specialized tools deal with it. So speaking of that, let me contrast like how Vespa works on Kubernetes today versus how it can look in the future. So this would be an example cluster, a relatively simple approach, but still like fault tolerant and with all the important bits and pieces. So we have documents and queries that would hit the stateless layer. Those are the stateless container nodes that I've been talking about, and they would forward the data to the content nodes, which hold the actual data. And then we have config nodes, which typically are co-located with Zookeeper, like there's an embedded Zookeeper. And then they can also, I mean, in a typical cluster, they would also co-locate with the cluster controllers. And then there's usually an admin server separately that runs the log server for centralizing logs. So in order to deploy a Vespa cluster on Kubernetes, you first have to bootstrap it. What does that mean? We have to make sure that the config servers are up before everything else. That's because we want to apply an application package which tells everything. So Vespa will have one image that will run on all the nodes, but initially nothing is started except for the config servers that we specify in the command line arguments, like here where I say config server services. So with the config servers up, we can apply the application package, and in the application package, we specify which node does what. Like we can say that these 2 nodes are stateless, these 4 nodes are stateful, right? And maybe this is the admin node. So all that goes into services XML, which has to match, obviously, what we have in the Kubernetes definitions, right? Because we can start 8 nodes here and expect 16 nodes on the other end. And there's a service that's called config sentinel, which once the config is being replicated, it will figure out, oh, I'm a stateless node, or I'm a stateful node, and so starts the appropriate services on that node. And then you have the cluster that you wanted. And this can change, this can simplify in the future, because, for example, if we had specialized images, like one for each service, then we can create the cluster as we wanted from the Kubernetes definition. We wouldn't need the services XML to specify which node does what, because we have that in the StatefulSet, for example. And this will also remove the need for a config sentinel to start the right services, because, again, we can do that from the definition in Kubernetes. All the monitoring and logging thing can be simplified. You know, like the logging could be just log to standard output, and we'll use external tools to deal with that. Same with metrics. We don't have to aggregate, because something like Prometheus or other monitoring tools out there can deal with the aggregation and just query every node in the cluster. And for completeness, there's another service that I did not mention, which is called the Service Location Broker. This one is used on the write path by the stateless nodes to locate the stateful content nodes. But this is not necessarily like in Kubernetes environment where we have services and we can do load balancing outside of the search engine itself. And that's all I had to share. The slides are up on Sched, you know. And you have a lot of resources there with regards to those processes that I just mentioned, the services, and also how you can run Vespa on Kubernetes. And I'm pretty sure we have some time for questions if you have any.
Does these config nodes talk to each other at all? Like which is the zookeepers in it?
Okay, so I'll echo the questions just so everyone is in sync. So the question is, how do config nodes like these talk to each other, and how do they know which zookeeper? Config nodes by default will embed zookeeper, and they will all make part of the same ensemble. So there's a zookeeper quorum that deals with all this. You can also use an external zookeeper, but again, it will be the same thing. All config servers will point to the same zookeeper cluster, and zookeeper will have quorum and leader election and all that stuff for consistency.
That becomes a bottleneck as you compared it with other things. So wouldn't that becomes a problem, like zookeeper is not that stable as we want it to be?
Right, so the question is if this becomes a bottleneck, because, as I said earlier with Solr, Zookeeper can become a bottleneck. I think it's less likely to become a bottleneck because here, in Solr's case, Zookeeper will hold everything, not only the config set, but also the state. Like, if a chart goes down, that has to be updated in Zookeeper by the overseer. In the case of Vespa, we only have the config. So only when you change, let's say, the schema or change the machine learning model, that's when you update it to Zookeeper. So you have much, much fewer writes to Zookeeper, and I don't think that is likely to be. I think no, I didn't know. Okay.
When you resharded the data, you compared it with Cassandra, when some of the B nodes actually moved from one to other, that information also goes to these configs, or how does that happen? Does other nodes need to know that information as well, like in Cassandra, the gossip need to happen and all?
Right, so the question is, how does this information, when we move buckets, how does this get propagated? And this goes back to the cluster controllers. So the cluster controllers will know that there's a new node in the cluster, and will know that some of the buckets are ready or kind of moving around. So they will have to be aware of that, and then they will sync up with these other process, which I did not mention, which is called distributor. So distributor lives on every content node, and they will talk to the cluster controllers, and they will know the updated state, and they will serve it during queries and such. That's how it works.
And can I add more than one node at a time?
If you can add more than one node at a time, yeah, I'm pretty sure. Yes?
This is little off, right? But what is the best embedding and splitting method for most accurate semantic search?
I'm sorry, I did not get the question. Can you rephrase it? This is like what?
What is the best method for embedding and splitting for most accurate retrieval?
What's the batch method? What's the best embedding and filtering method for? Oh, this is completely up to you. Like, you can choose whatever model you want for creating embeddings and at the search time. So we don't provide out of the box embedding models. There's like a Vespa embedder concept where you define an embedder in services.xml, and you can point to pretty much any Hugging Face embedder model that you want. Does that answer your question? Yeah, okay, cool. Any other questions? Yeah.
This is like specifically Vespa.ai. So are you like powering AI, or you have some AI features?
This is, yeah, specifically regarding Vespa.ai, that's the company name, and the search engine is called Vespa. So, yeah, this can power all sorts of applications, from RAG to recommendations to whatever, but we don't offer, at least at the moment, complete solutions for that.
How is the isolation in terms of like Elasticsearch provides isolation with the indices? So how is the isolation maintained with respect to your schemas or how is it?
So the question is, how is the isolation done? Because with Elasticsearch and Solr, you can have different indices or collections to have different, completely independent sets of data in the same cluster. And the question is, how is the isolation done in Vespa? It's very similar. In Vespa, there's this concept of document types, and each document type has an attached schema, and these would be separate files on disk. So when I say there's an index data structure per node, I was kind of lying in the sense that it's one index data structure per node, per document type, per field, because you're searching one field at a time. This applies to everything. Any other questions? I think I saw more hands coming up.
Can you explain the copy of the buckets? So when a new replica is brought up, do you just create empty buckets there, or you actually do the data copy?
Yeah, so the question is when we move the buckets around, like do we create empty buckets or is the data being copied? We create the empty buckets. I mean, we don't create the buckets, we move the buckets, but initially they're empty and data has to be re-indexed effectively.
The whole data has a fixed sharding space, right?
Yes, the whole data has, I don't know what's the number of buckets by default. 2000 then.
So now you have to update like whatever sharding technique you're using to
Yes.
distribute the data. How do you update that to account for this move?
So the question is, how do you update the what to account for this?
Distributed the data.
Yeah.
So if any new write now has to go to the new.
Yes, new writes will go to the same bucket because it's a fixed bucket space, but the bucket will live on the new node. So the new write goes to the new node.
And the old one is discarded.
And the old one, as they moved to the new node, they are discarded. And I think one important thing to mention here is that all this indexing and reindexing, whether it comes from the client or from data redistribution, is in real time. So if you add a new document, it's instantly visible to search. When you get the acknowledgement, it's visible for search. This is different than all the Lucene search engines where you have to wait for a commit. So I think that also facilitates this thing.
If we are facing any hotspotting on a specific node, and is there a way to redistribute these shards manually, or Vespa itself decide like which node, what shards goes where?
Okay, so the question is, if we do end up having hotspots, if we can redistribute buckets manually or things like that. Frankly, the answer is I don't know, but I can take this question offline and answer it. I don't know if I can put it in the comments or something. Yes?
Flow of request, just want to draw parallel to
Yes?
what happens with Elasticsearch.
Yeah.
Like request comes to the coordinator node and distribute the data and get the results. So for this, when you said stateless, so that acts as a coordinator for.
Yes, so the question is, if we go over the flow of what happens when you run a query, is that like if when you run the query onto distributed Vespa cluster, right? So that query will go to the stateless container node first, and then the stateless container node will know all of the content nodes, will distribute the request to all the content nodes, and the content nodes will each reply with one part of the response. So in this case, we have 4. Each one will reply with, you ask for top 10, each will give a top 10. And the stateless node, acts like a coordinating node. So it will, do any aggregation. So the only difference I can think of in the context of your question is that the response is per node, not per shard, right? With Elasticsearch, you can have multiple shards per node, and you kind of need to do that in order to be dynamic with scaling.
And is there a limit, like the shard has a limitation of, say, 20 gigs? So
Yes.
do you have such limit for your data?
No, because of the is if there's a practical limitation of shards of like, how much data can you put on a node? No, it's you can have pretty huge nodes because of the way it works with buckets and all. Yeah.
Vespa supports these kind of plugins like Logstash and things like that, what traditionally Elasticsearch. So Vespa has those kind of plugable modules where we can plug in data and then say, I do not know if it works with Kibana or some kind of another abstracted UI where you can look at all these different. Vespa provides its own similar way of
So if I get it right, the question is how well does Vespa support different plugins to do things like ingesting data or visualizing or maybe other changes. Vespa can be very easily changed, like you can easily implement logic at the stateless container level, so it's very easy to do things like, I don't know, query parsing or re-ranking and things like that. You're using all sorts of models. It is not that rich as Elasticsearch currently is when it comes to the ecosystem of external tools that can be used, like Logstash. I'm actually writing, and it's already there, a Logstash plugin for Vespa, so you can write from Logstash to Vespa. You can use it to reindex. You can read from Vespa and things like that. But I know with Elasticsearch, there's like a ton of tools. We don't have that much rich of an ecosystem. And when it comes to visualizations, again, not much you can use. You probably want to implement something yourself on top of the API at the moment. But of course, this is work in progress. Any other questions?
Is there any concept of master in this?
If there's a concept of a master, there is only at the level of the, what is it called, cluster controller, right? So the cluster controllers that handle the cluster state, they have to elect themselves as a master, to check out which, but that's kind of the only single point of, yeah. Any other questions? Well, if not, thank you very much for attending.